Good morning students. Today 3rd April lecture 1. In last lecture we have discussed two applications of Gauss law. In this lecture we will study third application of Gauss law. Field due to uniformly charged thin spherical shell. Field due to uniformly charged thin spherical shell. It is difference between shell and sphere. Okay, you have to find electric field due to spherical shell. Shell means it has matter only on its surface. It has charge only on its surface. So due to shell, you have to find electric field. So we will consider 3 points, 3 cases: outside shell, inside shell, and on the surface of shell. So first of all, we will find electric field outside the shell. See, it is shell of radius capital R. Charge is uniformly distributed on this shell. Charge is uniformly distributed on this shell. Having surface charge density sigma. Having surface charge density sigma. We want to find electric field at point P outside the shell. See, outside the shell at a distance r from center. At a distance r from center. So here we can write small r is greater than capital R. Okay, clear? We want to find electric field at point P. Now, to apply Gauss law, first of all we have to select one Gaussian surface. See, select Gaussian surface, one sphere of radius r passing from point P. A sphere of radius r. A sphere of radius r passing from point P. Now see, from figure it is clear. Each and every point on the sphere, on Gaussian surface, is at distance r from the center. Is at distance r from the center. So as distance is same at each and every point, magnitude of electric field is also same. What about direction? Direction is radially direction. Is in radial direction. If it is positive charge, then it is radially outward. If it is negative charge, then it is radially inward. So clear about magnitude and direction? Magnitude at each and every point on the Gaussian surface is same, and direction is in radial direction. Is in radial direction. Now how to find magnitude of electric field? See, for this Gaussian surface we will find total flux. We will find total flux. See, flux passing from Gaussian surface, phi is equal to integration E dot ds is equal to E ds cos theta. Now see in figure, what is angle between electric field and area vector? Positive charge is uniformly distributed on this thin spherical shell. So due to this positive charge, electric field is in radial direction. Electric field is in radial direction. Clear? Okay. Let's take one element on Gaussian surface here. We know that area vector is always normally outside. Area vector is always normally outside. So area vector is normally outside. So see, E and ds, they are parallel to each other. E and ds, they are parallel to each other, means angle between them is 0. Students, it is right for each and every element on the surface. It is right for each and every element on the surface. If you take element at any point, okay, angle between E and ds will be 0 because they are parallel. Okay, E is parallel to ds, means angle between them is 0. Cos 0 means 1. So it is integration E ds. E, again, electric field at each and every point on the Gaussian surface is same. So it is out of integration. So is equal to E integration ds. ds, it is total surface area of Gaussian surface. It is a sphere of radius small r. So integration ds is equal to 4 by r square. It is equation number 1. Clear? Now, flux passing from Gaussian surface with the help of this equation, phi is equal to sigma q upon epsilon 0. Where what is sigma q? Sigma q is total charge enclosed by Gaussian surface. Total charge enclosed by Gaussian surface. Now see in figure here. Charge is distributed on shell of radius r. Its surface charge density is sigma. Then how to find total charge? We know one equation. Charge q is equal to sigma into A. Charge q is equal to sigma into A. So it is equal to sigma. What is area of shell? 4 pi r square. It is 4 pi r square. So total charge. It is Gaussian surface. It is Gaussian surface. Total charge enclosed by this Gaussian surface is charge on this shell. Charge on this shell. And what is charge on shell? Sigma 4 pi r square. Sigma 4 pi r square. Okay, upon epsilon 0. It is equation number 2. Now compare equation 1 and 2. So E 4 pi r square is equal to sigma 4 pi r square upon epsilon 0. So E is equal to 4 pi cut. It is sigma upon epsilon 0 r square upon r square. Now again from this I can write sigma is equal to q upon 4 pi r square. So sigma is equal to q upon 4 pi r square. Put its value q upon 4 pi r square. 1 upon epsilon 0 r square upon r square. Then you will get E is equal to 1 upon 4 pi epsilon 0 q upon r square. 1 upon 4 pi epsilon 0 q upon r square. Yes, it is also equation of electric field due to point charge q. Due to point charge q. If I want to write its vector form, then E is equal to 1 upon 4 pi epsilon 0 q upon r square r caret, where r caret is unit vector in the direction of electric field. And if q is greater than 0, it is radially outward. If q is less than 0, it is radially inward. So it is electric field due to spherical shell outside. Now see one interesting point. E is equal to 1 upon 4 pi epsilon 0 q upon r square. I said it is also equation for point charge. For point charge. So from this we can say for all points outside the shell, the field due to a uniformly charged shell is as if the entire charge of shell is concentrated at its center. We can say that for outside points, electric field we have to calculate such that its total charge is concentrated at its center. So it is electric field due to thin spherical shell outside the shell. Now second case, field inside the shell. See, we have to follow the same method. It is shell of radius r, which is positively charged. It is positively charged, having radius r. Now we want to find electric field at a point inside the shell. It is point P. At a distance small r, inside the shell. Inside the shell means I can write r less than r. R less than r. So now again we will assume one Gaussian surface passing from point P. Again a sphere of radius small r. A sphere of radius small r passing from point P. Passing from point P. Now we will follow our method. Integration E dot ds is equal to sigma q upon epsilon 0. What is sigma q? Sigma q is charge enclosed by Gaussian surface. See, it is Gaussian surface. It is Gaussian surface. And charge is distributed on surface of shell. On surface of shell. So, no charge encloses by this Gaussian surface. No charge encloses by this Gaussian surface. Okay, here Gaussian surface encloses no charge. Means sigma q is equal to 0. Sigma q 0 means right hand side 0. Then integration E dot ds is equal to 0. Then electric field is 0. So remember, at each and every point inside a spherical shell, electric field is 0. The field due to a uniformly charged thin shell is 0 at all points inside the shell. At all points inside the shell. Now, three cases. Inside means small r less than capital R. Electric field is 0 at all points. Outside, when r greater than r, E is equal to 1 upon 4 pi epsilon 0 Q upon r square. On surface, if you want to find what is electric field on surface, you have to replace small r by its radius, that is capital R. Capital R. So E is equal to 1 upon 4 pi epsilon 0 Q upon r square. Clear? You have to remember these three equations to solve questions. Now E versus R graph. Okay, what is variation of electric field with distance? With distance. So see, it is E versus R. Remember, small r is distance from center. Small r is distance from center. Okay, E versus R. Here, it is center. Center means r is equal to 0. R is equal to 0 to r is equal to capital R. This region is inside the shell, and inside the shell electric field is 0. And inside the shell electric field is 0. On surface, when r is equal to r, it is maximum. It is maximum. Okay, and as outside E is proportional to 1 upon r square, E is proportional to 1 upon r square. As distance increases, electric field decreases. Electric field decreases. So it is variation of electric field with distance. Pause the video, write down in your notebooks. Knowledge student, you have to send notes on my WhatsApp number. For other school students, write down in your notebook and send notes to your respective subject teachers.